We are going to go ahead and do another example, 9.8. It states two hockey pucks of identical mass are in a flat, horizontal ice hockey rink. The red puck is motionless. The blue puck, oops, did not mean to do that. Sorry about that. Let me get that erased. The blue puck is moving at 2.5 meters per second to the left, okay? It collides with the motionless red puck. The pucks have a mass of 15 kilograms, so that's each. After the collision, the red puck is moving at 2.5 meters per second to the left. What is the final velocity of the blue puck? Okay, so we're going to do what we did in the last one. We kind of map it out. So our initial P, momentum, is going to be equal to M red, V red, plus M blue, V blue, and these should all have those on them. We are defining this way as positive X, right? The right is usually positive. So then these are all moving in the negative direction. Okay. So at first our red puck is motionless. So that means our momentum here is actually going to be 0 for red in the beginning. Okay. So our initial P is just MB times VB. Okay. Now let's look at the final. Final, we have the same thing. We have some MR, VR, okay, plus MB, VB, and we'll say like comma F, okay, for final. Okay, so we need to then set these equal to each other. So we'll get MBVB equal to MRVR plus MBVB comma F. Okay, and if we want to solve that for our velocity, comma F, we'll have MBVB minus MRVR, and this is initials, so we'll just need to note that, and this is final. Maybe we should put that in the beginning, just so that we know, oops, the mass will stay the same, final, this should be, oh, mass stays the same. Every time I see a B, I just want to put an I next to it. What the heck? There we go. All right. So, should be comma I and comma F. All right. So we have this portion. So I just moved that guy over, and now I'm going to divide by M sub B. Okay. So this is what we need to solve. So we have VB, comma F, equal to our blue mass, which is 15, and I'm going to just leave it in grams, okay, times the velocity, and the initial velocity is 2.5 meters per second, and that is in the negative I hat direction, okay, minus M sub R, which is again 15 grams, okay, times V sub R, the final V sub R, which is negative 2.5 meters per second, and that is in the I hat direction, divided by our mass, 15 grams. Okay, and this is, again, the mass of the pucks are all the same. Okay, it did state that. So now we can even see from here, if all of our masses are the same, they just kind of cancel out. So we have 15, 15, 15. They all cancel, And so we have a negative 2.5 meters per second I hat plus 2.5 meters per second I hat. Okay, so this gives us 0 meters per second I hat. So our final velocity of that blue puck is actually 0 meters per second, so it's not moving anymore. Okay, so it transferred all of its energy to the red puck when it hit it. Okay? All right, let's go ahead and move on with types of collisions. So there's a few different types of collisions I want to talk about. The first one is an explosion. So this is when we have a single object that breaks apart or explodes into multiple objects. Okay, so this would be like a firework, right? A firework is all put together, and then when it explodes, when it finally goes up high enough and explodes, okay, it breaks into smaller pieces. Okay, and in this type of collision, we have an increase in kinetic energy. Okay, increase in kinetic energy. All right, then we have an inelastic collision. Okay, this is when we have multiple objects, so maybe 2 billiard balls or something, and they stick together, forming a single object. Okay, so that is actually more like the track that we saw. We had 2 little carts on the track, and then they stuck together because they had magnets on them. Okay, so we had multiple objects, so 2 objects, and they collided, stuck together, and they formed one object. Okay, and in this case, our kinetic energy decreases. Okay, so our kinetic energy decreases in this case. But again, the total momentum of the system remains constant. Okay, we're looking at that system, the total momentum is constant. Okay, then we have a perfectly inelastic collision. Okay, this is when we have any collision where the objects stick together and will result in a maximum energy loss. Okay, so that means we have a maximum amount of kinetic energy lost to the system. Okay? Okay, then we have elastic collisions. That is going to be, again, when we have multiple objects and they collide and they bounce off one another. So that would be more like the billiard balls or the hockey pucks that we just saw. Okay? And they remain as multiple objects, so the number of objects doesn't change. Okay? And in this case, the kinetic energy of the system is conserved. Okay? So there's no energy loss of the system. Okay, so kinetic energy conserved. Okay, so I'm going to just put this here. It's exactly what I just said about the kinetic energy, but just in a different format. So in an explosion, okay, we have that the final kinetic energy is greater than the initial kinetic energy. Okay, so final is greater than initial. In an inelastic collision, we have that the final is less than the initial kinetic energy. Okay, but it's not 0. Okay, if it is 0, the collision is perfectly inelastic. Okay, and if the collision is elastic, our final and initial kinetic energies are the same. Okay, or kinetic energy is conserved. Same thing. Okay, so let's look at a problem. So this is example 9.10. It states that a proton collides with a neutron that has about the same mass to form a particle called a deuteron. Okay, it's been a while since I've had to say these terms. Okay, give me a break here. What is the velocity of the deuteron? Deuteron? Deuteron. If it is formed from a proton moving with a velocity 7 times 10 to the 6 meters per second to the left. Okay, and a neutron moving with a velocity of 4 times 10 to the 6 to the right. Okay, so this is very similar to what we've been doing. Okay, so we have before and after the collisions, we have P sub I. I'm going to go ahead and say that this is the positive x-axis. Again, to the right is typically positive. And it will be m. And since they have the same mass, I'm going to go ahead and leave it as just m. Okay, times v p plus m times v n. Okay, and I am going to say, I can rewrite this as this. Oops, v n. Okay. Now our final will have our total mass, which is going to be 2 times our first mass, right? Because there's 2 of them. So I'm going to say 2m, or this would just be m plus m. Just like what we did before. Excuse me. Times our final velocity of the deuteron. Okay? Alright, so let's go ahead and set these equal to each other. So we have m times vp plus vn equal to 2m vd. Okay, our masses cancel, so we don't really care about them since they are the same number. And then we can solve for our velocity, which is what we're looking for. So it'll be vp plus vn over 2. Okay? So we can plug all of that in. We have our proton moving to the left. That is to the right. What in the world? They got their left and rights backwards. We're gonna go off the figure. Okay. So they say that's left, sure, that's in the positive direction. Okay. So we're gonna say 7.0 times 10 to the 6 meters per second in the I hat direction, plus our neutron, and that's going to be negative 4.0 times 10 to the 6 meters per second in the I hat direction, and all that divided by 2. Okay, so we can plug that into our calculators. We have 7 times 10 to the 6th minus 4 times 10 to the 6th, and then divide that by 2. And we get a velocity of 1.5 times 10 to the 6th meters per second in the I hat direction. Okay, so it will be moving to the left, which in this case apparently is the positive x direction. I'm actually kind of surprised that they did that, but I'm trying to follow the book. Okay, so this is our final velocity. All right, so I'm going to go ahead and get started on this slide, and we'll probably have to start or finish it on the next video. But we will now take this into collisions in multiple dimensions. So as we know, if we hit a billiard ball, it's not necessarily going to go perfectly straight, right? In theory, that would be nice, but we do have some x and y values of the movement. Okay, so what we can do is we can write these expressions for conservation of momentum for the x and the y directions now. Okay, so we can break down that movement just like we did with forces. Okay, we could do the exact same thing, but now with our collisions and momentum. Okay, so we'll go ahead and talk more about this in the next video.